Dear audience, so we're back here from the coffee or whatever. We had a little break. And please welcome Robinett here on the stage with us.
Okay, welcome. Okay, thank you all for coming. It's great to be back here again a year later. And last year I talked about the RX888 SDR receiver and K9Q radio. In this presentation, I'm going to talk about both the evolutions of those and to start with an idea of what we are able to study and learn. What's the motivation for creating this system? And the motivation is driven by our interest in radio science and radio propagation. We've all been familiar with for 125 years that there's radio waves are reflected through the ionosphere. But with the introduction of GPS stabilized receivers, we now have, for ham radios, we now have receivers and transmitters that are so frequency accurate and stable that we can actually measure the doppler shifts of the radio waves as they propagate. So this allows us to study the interaction between solar weather and the ionosphere. And this is an area that isn't as well studied by even the academic radio scientists because of the difficulty of making measurements and doing them over a large scale. So ham operators, transmitters and receivers actually have a unique opportunity to contribute to radio science. And this is, but this requires a good transmit and receive system. I'm a part of another group, the ham side. This is Amateur Radio Science Citizen Initiative. This is a group funded by the American National Science Foundation. And its goal is to promote the use of having citizen scientists, like all of you here, are such citizen scientists, to encourage you to make scientific contributions using the radio waves and the systems that we use for our communications purposes. And that ham site created a device, a system called the GRAPE, which is centered on measuring the Doppler shifts from the American time stations, WWV, which transmits from Fort Collins, Colorado, central United States. And they've deployed a group of receivers. There's more than 100 receivers primarily around the United States, which record those signals with a great deal of frequency accuracy on the order, well, all these receivers are driven by Balkner GPS disciplines, so that they're microhertz accuracy and stability. So in order to make those measurements across multiple bands, WWV transmits across from 2.5 megahertz up through 25 megahertz. The receivers they had were only able to do one channel or 4 channels. So I realized that the RX888, when it's driven by a GPS discipline oscillator, could measure all of these bands simultaneously and record them to a global database that they maintain. So in this slide, we show some of the charts that come from the database recording. On the left-hand side, you're seeing 24 hours of WWV on 15 megahertz when it's received by, let's see, I don't remember which station this is. This is a station in Ohio, so this is something like 1,000 kilometers away. So the scale vertically is, I think it's 5 hertz plus or minus. And there's an amplitude chart which is linear. Unfortunately, it's a linear amplitude chart. By adding capability to measure and record these the carriers from WWV. In the RX888 Wsprdemon system, we were able to put the same measurements into a database of our own, a proprietary database, an example of which is you see on the right. This is a Grafana page from our open source database, so it's publicly available to you. So why would you want to do this? What do you learn from these little perturbations of the frequency of the carrier? Well, as an example, I'm going to show you on this next page, my collaborator, the Gwen Griffiths, G3ZL, took these charts from an event that occurred on the first day of Hamvention in May 17th. There was a real major solar ejection that actually targeted the north central part of Canada. So by looking at these charts, there's WWV is here, the transmitter is here in the center. I don't know if my cursor shows up here. Here, does it show up? Yes. Here's the WWV transmitter in Colorado. And we took these great measurements of the transmitter's frequency at 4 different receive sites. There's a receive site up here and up in near Seattle, Washington. There's one in North Dakota, one down here in Texas, and another down here in Arizona. Each of these receive sites were recording the frequency of WWV for the 24 hours a day. Well, each one of them showed the perturbation, the motion of the ionosphere when that solar event hit northern Canada. It bounced on the ionosphere. The ionosphere actually moved as a result of it. And not only were we able to see it move, but Gwen was able to establish the direction and the velocity of the wave, a wave-like motion that occurs. These are called traveling ionospheric disturbances, and they're of great interest to the scientific community. So we're looking here at an event by looking at when the wave passed at this point, and then when did it come here. We're able to determine the vector and the velocity, how long it took by looking at the time between these two, the wave when it first moved the frequency here, and then when you some minutes later it showed up down here. You got a vector of 120 degrees in this direction, and a motion, a velocity of almost 600 meters per second. Similarly, along this other path, this from North Dakota, we had 2 measurements. One at this time, we saw the wave again appear down here at some time later. We established that was in that vector. We had a motion of about 600 meters per second along 221 degrees. So doing a vector sum of those 2 calculations, we came up with the velocity of the actual wave, the ionospheric wave. This wave was moving at 800 meters per second along a vector of 172. It was almost directly, the ejection, the solar ejection, hit just about in the middle of north of Canada, almost directly north of WWV. So this is only one example of the kind of information that we can now extract from, well, in this case it was WWV, but the same information actually can be extracted from ham signals, specifically WSPR2, and even more specifically, the FST4W variant of WSPR2. That FST4W transmission, those beacons, of which we wish there were more, but there are dozens of them now that are in service, those beacons actually allow us to obtain the same information, but they can be distributed all around the world. So one of my missions to come here is to propagate or inform you and encourage those of you who are interested in looking at the science of radio and the ionosphere and how the sun interacts with us in our world, to encourage you that this might be an area of interest, and either by setting up receive sites and or transmit sites, you can contribute to a greater understanding of how the solar weather interacts with our world. So to go back to so the goals of the system are to create a system that allows us to make these kinds of measurements. And these are only one set of things that we could learn about the ionosphere that we utilize for shortwave transmissions. So another example of insight that we can gain is we could actually, one of the things we learned in the last year is it's very useful to be transmitting and receiving simultaneously on as many bands as possible. What motivated this was, that if you're a user of WSJTX, you know that it works only at one band at a time. So if you go into whisper mode, it transmits, you can set it up to transmit sequentially, 2 minutes on 80 meters, 2 minutes on 40, and so on. A lot of solar events especially, but a lot of events in the ionosphere happen more rapidly than that. And a good example of such an event was the two eclipses that we had in North America in the last year. The eclipse totality lasts only at most for, maybe occasionally they're 6 minutes long. So if you're transmitting on one band and then moving to the next band, you're going to only you're going to miss any information about what happened on the other bands. You're only going to get 2 or 3 bands of information. This is like Nyquist subsampling. You're going to get aliasing. You're going to miss a whole bunch of information. But if you transmit simultaneously, we have many receivers, but in this case, the 888 is the prime example, where you can receive on all bands simultaneously. It's easy. Doesn't even take a lot of CPU power to do so. We needed a transmitter to transmit on all the bands simultaneously because we had an October eclipse that was only going to last 4 minutes. So Paul, WB6CXC, who operates the Turn Island systems, created such a transmitter. We had a prototype last summer, and we deployed 6 of them along the path of the totality of the eclipse in October. This map here shows the path of totality, which is in this this blue line, the eclipse annular. Let's see if I get my cursor back here. So what did we learn from this? Well, one of the things we were able to learn during this event, because we were actually transmitting on 80, 40, 30, 20, okay, we didn't really know which bands would be affected by this event and by how much. And somewhat surprisingly, at least to me, it was surprising to me that we saw almost no effect up on the higher bands, even 20 meters. But we saw a lot of interesting effects on 80, 40, and 30. And the change in the Doppler shifts from what you saw before on the previous chart, from those, Gwen was able to establish how much did the ionospheric refraction height, how much was it affected by this 4-minute long event. And you can see that in the chart on the right, you can see that the height of refraction moved by, I think, over 35 kilometers during that event. So that's a pretty major change in the ionosphere It's kind of like ringing a bell versus kind of rubbing a wine glass, is that this sudden disruption of the solar flux, in this case, produced a dramatic change in this. So part of our effort has been to make sure that we can correlate the measurements we make with these systems, correlate them with other measurement techniques that are used by the radio science community, specifically the ionoson measurements. Those measurements this has been going on for, I don't know, probably almost 100 years. I think ionosons are distributed around the world, and they probe the depth of the ionosphere by sweeping signals across the shortwave bands. And if you move your SDR to 3 to 30 megahertz, you'll see the diagonal lines, one or more diagonal lines going across the spectrum, which are ionosphere lines. One of those measurements, Gwen went and correlated what those measurements, which are publicly available, with the measurements we got from our GRAPE and our AIX888 systems. And you can see there's very good, the red dots being our measurements along the path. Now, I drove 1,000 kilometers to go out and set up this transmitter out at WS7I. And I was transmitting there. And so the red dots represent the change in height that was calculated from the Doppler shifts and from that path. And the blue line represents the calculations made from the WWV and GRAPE transmissions that were going in a different direction, but along the same path. So one of the interests, this is just the first page of a very long study that Gwen did, in which he was able to, among other things, establish not only the depth of the change, but also the different change in depth for different bands. So anyway, this is the kind of my purpose of this part of the talk is to give you a sense of why would we want to have transmitters and receivers that cover multiple bands simultaneously, and why would you want to why would you want to be able to do this in other parts of the world? So on the receive side, we built the system. Really, it's a software addition to the AIX888 system that I described, I think, last year in this, at this conference. This is, an AIX888 attached to some kind of a Linux host. Running the K9Q radio software library, which we'll be describing later in this afternoon. And of course, my Wsprdemon software, which then processes signals coming out of K9Q radio. So in order for this system to be part of this HAMSI GRAPE measurement system, it needed to be relatively inexpensive. I think the 888 certainly qualifies that. I've been able to, in the United States, buy them from Japan for China, direct from China, from about $160 US. It does require enhancements. The 888 itself is not as it's delivered, it has a 60 megahertz low-pass filter. That's not really suitable if you're only looking at a 30 megahertz bandwidth. So you need that, in addition to a low-pass filter, a 30 megahertz low-pass filter, you need some gain. These wideband SDRs, at least the two I know intimately, the Kiwi and the AIX888, both have relatively poor noise figures, and which means that they really need a low noise amplifier ahead of them. And then, of course, once you do that, then you have the issue of overloading. and especially that's especially an issue here in Europe. So we have Paul has developed a kit. There's also, of course, the need to adapt the 888, which has a plug on it for the external oscillator input, but it's very easily damaged. You can easily, I've blown up a couple of my 888s by connecting them or misconnecting them to external Wagners. So Paul has developed a kit which is now available that adapts, insulates the Wagner's signal and conditions it to put it into the external clock input of the 888. The other issue with the 888 is that it has a thermal problem. It gets very warm as delivered. So we have a thermal pad modification for the 888 that is available as a kit. And in fact, I brought one here. Did I give it to you? Or well, here, I'll show you. This is part of it, at least. These are very simple. I think it's available from Capper in the U.S. For $30. It has a little circuit board on it that goes inside the 888. There's a new back panel and a thermal pad. It takes no soldering required. If you have a 888, you really need one of these. Be really careful with your 888 unless you have, especially Paul's interface printed circuit board. It's very easy to damage it. That being said, in $30 in US and in 15 minutes, you can adapt you modify your 888 and solve all those problems. So similarly, like any wideband SDR, it needs more gain and it needs a filter. So this is one of Paul's filters, which he developed to address the need for a 30 megahertz low pass anti-aliasing. So we have a very simple, with simple modifications, you can make the 888 to solve its problems, hardware problems. Of course, you need a GPSDO. Well, that's Tapper is working on one for somewhat lower cost than the Wagner, but I think we all know the Wagner. And of course, the rest of it is software. K9Q software is open source from GitHub, as is my Wsprdemon. You need a host. Surprisingly modest host. It's amazingly, Phil's software is incredibly efficient. You can run it as 66 megasamples and decode and output literally 100 different receive channels to 100 different things on a 10-year-old i5 6500 class CPU. You could buy them refurbished for $89 on eBay. It can easily handle the computational requirements. So this architecture is very software-centric. I mean, Phil's library is really the core of the signal processing chain, and enables the whole these applications. So this is an example of a kind of a complete whisper, grape. And in fact, I have a super darn mode. There's these transmissions that are ionospheric radars that are around the world. I can record those too. So you can get an idea of how small this is, how inexpensive it is. And really, we've now 20 of these running around the world, and or more than them, contributing continuously. So this is, our problem really with this system is almost all of them, except for a few experts here in Europe, almost all of them are North America, which means all of the measurements we make tend to be centered in the northern latitudes, in North America. In the radio science community, very little is known about the ionospheric events in the southern hemisphere. So we really want to encourage international attendees and viewers here to consider the opportunity to contribute to the radio science by deploying receivers in the southern hemisphere. Michael's working to put one, I think, down in Antarctica next January. But we literally have thousands of transmit and receive sites. There's 3,400 whispered beacons in operation, about that every day. There's 1,800 receive sites. I would say 90% of them are in North America or here in Europe. We need maybe 95% of them. I mean, it is, we have one other than when we get Antarctica working. The only other one in Southern Hemisphere is Phil Barnard, VK7JJ in Tasmania. We need more, and there's a lot of interesting magnetic and other geological events occurring in the Southern Hemisphere that we don't know anything about. Anyway, here's the filter section. Paul is working on adding an LNA section to this, so that it would be an LNA, a 10-15 dB of gain in front of it. Typically, the noise figure of a Kiwi is about, I think it's about a 17 dB noise figure, which is a good, that means a Kiwi is 6 or 7 or 8 dB noisier than what you'd get off of an antenna in a quiet rural location. So on the higher frequencies, 20 meters and above, you're listening to your own noise. Most, at night certainly, and in quiet times. The 888 is even worse. It's more like a 20 dB noise figure. So both of these devices, I think, would absolutely require that there be an LNA if you have a quiet receive site. That's a whole subject I could go on for a whole talk about. So we now have a receive system. Relatively inexpensive. It covers the whole of the amateur bands. You can do 2,200 meters. Actually, the 888 will sample at 128 megasamples. So you can go up through 6 meters on one device. If you have an antenna and an LNA that can condition the RF fed to the 888, you can receive all of the amateur bands up through 6 meters on one receiver at one time. And I'm doing it on one of those $89 Lenovo i5-6500s. The refurbished things has enough CPU power to do it. So it doesn't take a lot of CPU at this point to do software-defined radios. So we needed a transmitter. That, as I said, especially for the Eclipse event, but there are a lot of other solar weather events that would benefit from having a transmitter. So Paul created what is now in the production mode is what's called the whisper sound, analogous to ionospheric. This is an 8-channel output transmitter, whisper and FST4W transmitter. It simultaneously outputs 1 watt on each of its outputs. So it does so continuously. So there's no band scanning here. This is simultaneous transmission across the whole of all of the amateur bands. Of course, you need an antenna, and you need a way to combine all of those outputs together. So so there's also a combiner that goes together. Of course, you could have 8 different antennas, 8 dipoles, each with its own feed line. That would be optimal, but a lot of trouble to erect. In a more practical sense, many hams already have multi-band antennas. I've used and deployed end-fed half-wave, 80-meter half-wave, which in its modified form works quite well all the way up through 10 meters. So on one, log antenna, it's a 40-meter long piece of wire. but I can do all the bands. It's resonant on all the bands simultaneously. But but in order to feed such a antenna, Paul has created a couple of combiners. The one you see here is this small box on the top of the whisper sound. This is a 6-band combiner, so it takes an 80 meter 1 watt signal, 40 meter, 30, 20, 15, and 10. I think is the. It'll do six bands, put them all together, and feed them into one antenna. So you can have one antenna transmitting on all the bands all the time. So this is kind of the partner, the source for the what you would do on the receive side, with the receive antenna. Receive antennas aren't so sensitive. You don't need to have a resonant antenna to do a good job receiving. You can. But on transmit, you want to, efficiency of your transmission is dependent upon the quality of the resonance and the matching of the antenna. I mean, the whisper sound will drive an open. It doesn't do well on shorts, but it will do. It will tolerate them. But so this is an in production device. We have them deployed at about 6 sites around the U.S. And hopefully by next winter, Michael will have installed one down in Antarctica. So the more of the transmitters we have, of course, these are kind of analogous to having WWVs, and the kinds of measurements we made. I showed you in terms of how a solar event affects the ionosphere. When they happen in the southern hemisphere right now, nobody sees them, and so we're missing half of the events, probably more than that, because we don't even get all of the northern hemisphere. So this is available. Paul has some in stock, and if those are interested, it does require it requires a Wagner in order to discipline his oscillators. It produces a very high quality output. As you can see, this is his spectrum. Of course, this is after the filters. Okay, I mean, these are square wave outputs, but they're going through these bandpass filters. So once you get through them, you can see that I think he's the worst spur is about -57 dB below the carrier. So. It's very high quality. It's it's 5351, like almost everybody uses. He is using a new algorithm, new to us at least, not I think to the mathematical community, a continuing fraction algorithm, which calculates the values for the 5351 to generate carrier frequency, tone frequencies with microhertz accuracy. It's remarkable. But there's certain frequencies where there's phase noise problems, but in general, the frequency accuracy is, when you go to his status page, he reads out the transmit frequencies to the microhertz, because it's entirely determined by the accuracy of the Wagner. On the right, he's just showing you, I think we saw an example earlier of the difference between Gaussian modulation, which is the technique used in the 4W mode, uses Gaussian mode frequency shift keying, which produces a much cleaner. It reduces the sidebands that are present in Whisper 2 transmissions. I don't think that either of these are this is a particularly big issue in the Whisper world. The sidebands in the standard Whisper FSK are typically still down below the noise, so it probably doesn't produce a lot of interference. But that's this gives you hopefully gives you an idea of the quality of the transmitted signal. Its frequency is as accurate as a Wagner. Its spectral output is fully compliant with the requirements of our regulatory and systems, and I think you'd find, if you would find these devices, when you'd be quite surprised if you look at the top beacons around the world. When we had these in Whisper 2 mode, all of the top beacons were Whisper Sound 8. Now, in a sense, it's unfair competition because you're transmitting on 8 frequencies simultaneously. So obviously, you have the potential to have 8 times the number of spots recorded for you. But a site that was, we had one site during the October eclipse transmitted on 8 bands and had almost 500,000 spot reports over a 24-hour period. Represented 10% of all the spots recorded. During that 24-hour period. So that's one transmitter in Texas. So there's actually, the goal here is not to be the top of the top beacons list or top spotters list. Each one of those spots represents a measurement of our ionosphere and the motion of the ionosphere and its behavior. And so our goal is not to just, you're welcome to compete in that way, and some Whisper receive and transmit sites do gain, the pleasure they gain is from being at the top of the list, having the most spots. But for the scientific interest that I have and others have, our interest is really trying to get more spots in order that we get more measurements, so we have a better insight into the interaction between the sun and the Earth and our ionosphere that protects us, really, in many ways from some of these rather dangerous emissions from the sun. So I would hope that if this interests you, if participating in this, you'd go, if you can, of course, go to HamSci, the group that I've taken this from the presentation I gave to them a few months ago, hamsci.org. Our site, Wsprdemon.org, where we have a bunch of papers where we show you what we have come from, what you've learned from these systems, what we can learn. There's much more. There's so much data now that we're just overwhelmed by things that we wish we could investigate. We don't have time. Paul's site, turnislandsystems.com, is where you can go to see about his Whisper Sound 8. And the Tapper is offering these kits. They have at least the ARX AAA kit available for immediate shipment. So those are those are what I hope I've communicated. Not too much and not too much of confusion to you. I hope I've communicated my excitement about how interesting I find this scientifically and intellectually, and amazingly socially. One would think these are computers talking to each other. This is a beacon sending a signal and it's getting recorded by some other computer someplace else. So, is this real ham radio? I have never had so many interesting new friends who share my interest and who we collaborate, we meet weekly. It's been a tremendous social benefit for me. And so if I can communicate to you some of the excitement that I've had from working on this over especially the last couple of years with this HamSci and these measurements, I really hope that you might consider looking into it and joining us. Okay, do we have any questions? And of course, you'll see I'll be here till the end of the day, so you can catch me outside if you have any other questions.
Thank you very much.
Okay. Did I run over my time? Oh, sorry.
So, excellent, fantastic. I'm enthusiastic about that because it allows us to see the ionosphere worldwide in a completely different way. And this is really inspiring research. So we've run out of time a little. We need to start the new slot right at 14:50. But there is more to come, which I can promise you. And also to you, Rob. Okay, we need to build up a certain amount of things now.
If we have any questions for
we can use the time in a few minutes.
We can try to fill the gap. Any question on Rob's? Yeah. Rob, pay attention.
Is it also possible to measure group delay between the 6 different bands of your antenna?
Closer to you. My hearing is really bad.
Is it possible to measure the group delay between the 6 different frequencies?
That's the next challenge. So we have, okay. In this, what we've done. Here, it's on. Do you hear me? Yes. We have, this effort in the last year has been to achieve its frequency accuracy, okay, and stability, okay. The next challenge is there are 2 more challenges we're aware of. One is to attempt to identify the path of the transmission time, how long it took the transmitter, the signal to go, and also what is its path, okay? They kind of go together, but they not entirely. The other dimension is phase, okay, is to understand the phase of it. Both of these, phase can be studied with, synchronized receivers. And there's some efforts underway to develop a kind of extension of the ARCS 888 architecture, a dual 888 with a common clock and a well-defined, transmission delay time through it. So that's one path. There's some people working on. The other one is to measure group delay. You can't really use the whisper modulation technique. The baud rates are so low, there's no way to measure it. So it's to measure the group delay, the transmission time, is going to require a new modulation technique. And that's
I have to interrupt. I'm very sorry.
Yeah.
Since we are running out of time, Rob, but you mentioned the right word. With the SDR technology, we are able to create new modulations to study effects which we haven't thought before. And this is a very important step forward.
I hope we can come back next year and talk about that.
Okay.
Okay. Thank you.
Of course.